metals, Professor Wetland. So, if we start as a general review of all topics, so we will start with the metallurgy and alloys, with primary remarks, classification and selection of material, atomic structures, and bonds types, crystalline structure of metals. Then we have real crystals, slightest effects, microstructure formation, diffusion, phase transformation, phase diagrams, fundamentals, Wittig transformation, and iron carbon phase diagram. In the second part, heat treatment, we will have temperature and Morty diagrams, heat treatment of steel, precipitation hardening of aluminium. In third part, ferrous material, we will discuss influence on residual and alloyed elements in steel, standardization and datation of ferrous material, steel cast iron, influence of alloyed elements in aluminum, standardization. Part 4, we have deformation plasticity. So plasticity, slip planes and slip systems, dislocations, hardening, recovery and recrystallization. In part 5, we have exertion recycling. With points iron, steel extraction, aluminum extraction, copper extraction and recycling. In part 6, material testing and failure analysis, we will have metal topography and microstructure, material testing, material failure, so wear, fracture, fatigue, and corrosion. In non-metallic materials, we have ceramics and glass. And that's it. We will look into example exam, which is provided. Then we have two more additional practice tasks. So we will see those later. And we will have in total 11 presentations. So we will start with metallic and non-metallic materials. So material testing part. We have documentations. Preliminary remarks. Materials classification and selection in professional practice with design engineer. A sensible choice of materials is decisive for the price and quality of the component. Everything consists of material, atomic structure, and all mechanisms of physical systems can be traced back to interaction of atoms. So we can understand macroscopic systems without knowledge of the microscopic state. So it's crystal structure of metals. This metals essentially the arrangement of their constituent atoms. This arrangement is periodic. The phenomenon of practice can be better understood by knowing the internal structure of material. So integration of material engineering into other disciplines. Material classification and selection. So For metals, we have ferrous materials which contain the right and non-ferrous material. So in ferrous material, we have very common steel and cast iron materials. So example of steels are structural steel, tool quill, temperature, heat temperate steel. In cast iron material, we have cast iron, malleable iron, and cast steel. In non-ferrous material, we have heavy metals with a density larger than 4.5 grams per centimeters in a certain degree, and light materials with a density less or equal to 4.5 grams per centimeters cube. Examples of heavy materials are copper, zinc, and lead. For light materials, it's aluminum, magnesium, and titanium. The non-metals have parts natural and artificial materials. So natural are granite, rock, asbestos, wood, and artificial plastics, glass, and ceramics. And we have composite material with reinforced plastics and metals. Materials still article is one of the most important material. Non-ferrous metals are all metals that other than iron, as well as metal alloys in which iron is not the main element. So material properties are high electrical conductivity which decreases with increasing temperature, high thermal conductivity, ductility or formability, metallic gloss, mirror finish. And steel is an iron-carbon alloy containing less than 2.06% by mass carbon. Cast iron is a group of iron alloys which is a high proportion of carbon, more than 2%, and silicon, more than 1.5%, as well as other elements such as manganese, chromium, or nickel. So the reason for using non-ferrous material are corrosion resistance, high temperature and strength, corrosion and scaling resistance, low density, and electrical properties. So root cause is cohesion of atoms by metallic bonds, periodic arrangement of atoms in the form of lattice, electron modifying freely, going freely in the lattice. So called electron gas. So we have two base groups of classification, so construction, structural materials like a concrete, steel, aluminum, titanium, magnesium alloys, plastics, and ceramics. And we have function material like copper, silver, gold, silicon, zinc, sulfur, so silicon dioxide, and others. So electrical line, semiconductor, gas sensor, piezoelectric, optional conductor, transformer, plate. So why do materials have different properties? So there are different type of atomic bonds. So primary chemical bonds like ionic, covalent, metallic, and secondary bonds. called van der Waals bonds, dipole formation, permanently or momentary, hydrogen bonds. And we have different types of atom order. So it can be amorphous, crystalline, and crystalline ordered. Structure, types of atomic bonds. So electron structure, the number of electrons and protons is equal, so filling up to the potential field. Energy states are discrete. There is no room for two n² electrons in the nth shell. Planetary, so it's a planetary or Bohr model, and the periodic table of element used. So here we have example of, let's think, atomic model. So with distance r, energy levels, so it's 5 energy levels, and electrons modeled. Concentrate on metallic bonds. So atoms share electrons. So it means electrons are evenly distributed or delocalized. And it's electron gas model. So there is no preferred direction in bonding, and metallic crystals are closely packed. Here is another important part about bonding force and atomic structure. So we have a distance scale force. So attraction, electrons, energy reduction. It's between atomic nuclei and electrons. So with larger distance, the force between atomic nuclei and electrons attracting is less. So we have a repulsion, so between atomic nuclei and other atomic nuclei, and between two electrons. So with distance increasing, it increases. We have force equilibrium. Force equilibrium distance are 0. And we have bonding energy. So difference between the energy of an isolated atoms and its energy in the bonding. So bonding energy is equal to isolated energy minus its energy in the bonding. And we also have here force. Here, let's for the score. Formation of electron gas. Splitting of the energy levels when atoms approach each other. So it means electrons, the outer shells can move freely. Called energy band. Crystalline structure of metals. Composition and structure of metals. Hardness, deformability, etc. are macroscopic phenomena, or they can be best explained in macroscopic scale. So in range centimeters, so for 10 to the minus 2 meters, it is necessary to zoom to the grain size range to uncover the initial mechanisms that affect strengths. So in micrometers, and it's only in the range of atoms, and the arrangement in the crystal that the underlying mechanism become truly understandable, so range in nanometers. Structure of lattice crystal lattice model. So here in the picture we have primitive cubic lattice and unicell. So attractive and repulsion also forces between metal atoms are at equal distances, and in this condition we have a formation of an internal order called crystal lattice. Experimental analysis by diffraction images, description by models, three-dimensional point lattice. So the unicell describes the regularity of atomic order in a three spatial direction. So centered cubic lattice or FCC. It can be in unstable arrangement, so a small force can shift the upper plane to a more favorable position, like here. So it's a model of primitive cubic lattice. At the bottom we have stable arrangement. In stable arrangement, the reduced height, so it's improved packaging density, and the face center cubic lattice grid is created. The maximum space filling for face center cubic is 74%. So energy minimization, so it has a stable configuration, and plastic deformation occurs preferentially in planes with the closest sphere backing, so-called slip planes. So slip planes with the closest sphere backing. Here we have a visualization of octahedron plane. So here's a cube and this diagonal plane. Slip removal of a corner atom in CFCC unicell. So closest sphere backing FCC will continue. So position of the face-centered cubic unicell in relation to the planes of closest sphere backing. Subsequent lower snaps into the gaps of the previous law. Here we have example of ABC face-centered cubic lattice. So here are layers CBA stacking. So they snaps into the gaps here. So, and these three are octahedral planes. And we have a third type, HCP, hexagonal closed backing. The structure is cubic and hexagonal closed backing represents the densest backing of equally sized atoms. Both lattices differ by the different staking order. So for face-center cubic, it's ABC, ABC, and for hexagonal closed backing, it's AB, 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 and so on. So the hexagonal, so in HDP liter, hexagonal closed backing, we have AB, AB structure. The octahedral planes of the face-centered cubic lattice are constructed exactly like the base planes of the the hexagonal closed baking lattice. So this A part is similar to this. And we have another type of the center cubic lattice, PCC. So formation from the cubic community plates lattice by occupation of the lattice vacancy in the center of the unit cell. So less space filling than for this center cubic lattice. For hexagonal closed baking, there are numerous lattice gaps and high absorption capacity for small impurity atoms. And we also have coordination number of a center cubic lattice. Coordination number is equal to 12. For PCC lattice, it's 8. Here we have some notation. For the most important type of bonds, so they are ionic atomic metal and secondary bonds, so van der Waals and hydrogen, and special arrangement of atoms. There is a crystalline amorphous structures which influence properties of material and components made of them. So properties of the various atoms and thus the elements of periodic table result from their subatomic level. So it was 10 to the minus 6 meters or micrometers. And this is determined by quantum mechanical principles. So combining crystalline structure and electron gas model, we can describe characteristics of metal like formability, thermal, electrical conductivity. So crystallines are formed by a periodic arrangement of atoms, and this structure is a result of the formation of an equilibrium distance between the atoms. So the type of crystals, we use the excretion by elementary or unit cell, the most common lattice types, center cubic and hexagon closed baking. So those are close baked, around 74%. First, we see and the lattice type with the center cubic. Physical importance plates of closed baking. Atomic motion occur preferentially in these sliding planes. So, the second lesson, real structure, real crystals, lattice defects, alloys and structure formation, diffusion and phase transformation. So according to practical relevance, we have real crystals. So diffusion from the ideal structure are characteristic for technical materials, metals. Alloy formation. Raw materials have minimal technical significance. For instance, ferrum. The quality of material and thus the product made from it depends strongly on the correct selection of alloying elements. Diffusion has specific changes in material properties are often based on or partially on diffusion processes and phase transformations. One of the most important phase transformation are often the basis for achieving desired material properties. Phase transformation are characteristic for heat treatment. So Real crystals, lattice defects. Real crystals are characterized by crystal structure defects, inhomogeneous element distribution, also called segregation, precipitates, different phases, and internal stresses. So we can divide crystal defects um, for different dimensions. So in zero-dimensional crystal defects, it's called a point defect. So it can be point, impurity atoms, like here. In one-dimensional crystal defect, we have dislocation. So like here, so there are 6 atoms, it's in 5, and it's a dislocation. And in two-dimensional scale, we have crystal defects on grain boundaries. The two-dimensional crystal effect can divide in more groups. So when we have a large angle boundary here, the crystalline materials consist of a structure of monocrystalline grains. And here we have a small angle boundary, subgrain boundary. So subgrain boundary, the single grain is subdivided into subgrains whose orientation divided from each other by angle less than 15 degrees. So we have here a twin grain boundary also. Twin boundaries are large angle grain boundaries. At the twin boundaries, the crystal is mirrored. And its sticking faults. We have sticking faults or errors in the sticking sequence of the hexagon post-packing base-center cubic grid. In precipitates, it's in a 3D scale. We have such defects like a coherent phase boundary called GP zone, partially coherent phase boundary, and incoherent precipitation. Coherent phase boundary or GP zone, similar phases can form coherent or partially coherent interfaces. So in partial coherent phase boundary, coherent and partially coherent phases are formed during precipitation process. And incoherent precipitation, it can be artificial aging, so elevated temperature, or aluminum to cuprum alloys, formation of incoherent data phase. And structure formation. So alloy formation, metallic materials usually consist of several metallic elements. Alloying elements determine the crystalline structure of the material and targeted adjustments of cell properties. So alloy formation, two types of crystals. It's a salt solution, crystal mixture. In salt solution, it's the inclusion of certain amounts of other atoms in the basic matrix. It can be substitutional solid solution, interstitial solid solution. Crystal mixture is, for instance, varied to very light. and we will see it later. So solid solution, substitutional solid solution. Atoms A on the base lattice exchanged or substituted by foreign atoms B. So here we have single phase A lattice, and here B statically distributed in A lattice. So this again circles. Kepler's miscibility, all A atoms can be replaced by B atoms. And heuristic, same lattice type, similar atom diameter, and we have limited miscibility called miscibility gaps. So it was a substitutional solution. Here we have interstitial solid solution. So a small non-metallic atoms can be stored in the material like hydrogen, nitrogen, carbon, boron. Relevant. The solvability usually smaller than 1%. So here we have main atom with large diameter E, and one small interstitial atoms with diameter small d of atom, and F is equal to small d divided by large d less than 0.51. Crystal mixtures, heterogeneous microstructure. So crystal mixture is always with several types of crystals. The different phases can have different properties, sizes, and shapes. So for instance, in the first case, complex structure, we have one first phase and second phase. So described in these grains, we can have second phase dispersed. We can here observe the grain boundary segregation. So here phase 2, the grain boundaries, and the last elongated secondary phase. So alloys. Alloy is a mixture of metal with one or more material. With one or more other metals or non-metal. Chemical components of metal, ABC, or from silicium of Lazarus concentration is a fraction of a component in mass percent. The mass content WA component A. So for instance, the mass content WA is equal to MA, mass of component A, divided by M, total mass. So mole fraction X with index A of component A. So the mole fraction of component A, it's A is equal to NA, the mole count in unit mole of component A divided by N total. System all alloys compositions that the component can form. Phase is a summary of all components of a system with special constant physical and chemical properties. So homogeneous is a one phase and heterogeneous two phases. Values of the state variables determined by phases with component content, temperature T, pressure P can be also, and contents X. Diffusion. Diffusion is characteristic, so it takes place inside thermal motion, particles, atoms, molecules, or charge carriers. So in uneven distribution, statically more particles move from areas of high concentration into areas of low concentration, then vice versa. So it's a main principle also used in chemistry and biology. Net macroscopic mass transport takes place. Fusion is usually understood as this net transport. Diffusion can lead to both mixing or segregation, responsibly depending on which state is energetically more favorable. So it's also these transformations. Thermodynamic equilibrium transitions, equilibrium conditions and phase transitions. Material are phase systems. Each system is assigned a unique state at a given temperature. Can be also pressure and section. When the state is reached, the system is in equilibrium. A change of this equilibrium state is only possible by a change of the system condition, for instance, temperature and or composition. Change of states of aggregation, for instance, liquid to solid, are called phases transition. Phase transitions are change of state aggregations. Phase diagrams, fundamentals. Phase diagrams, depiction of the phase in which a material can occur as a function of temperature and chemical composition. Prediction of material behavior from knowledge of the physical state. Planning of heat treatment process. Optimization of material through suitable alloy compositions. So, in diagrams, we have state variables. A system state is characterized by state variables, so it's temperature, it's relevant, temperature, so it's in kelvins, it's large T, and it's y, it's in Celsius, usually position or concentration, C. And as we have seen in the second lecture, the concentration, for instance, for component A is equal to mass of component A divided by total mass of alloy or all material. Structure transformations. Macrostructure transformation can be like a solidification, dissolution, precipitation process, transformation processes, formation of new phases. So they are associated with the various variation of the state variables. Normally pressure is around 1 bar, so it's environmental pressure is irrelevant. So each state of material can be described by a pair of values, temperature and concentration, as it should be called. So phase diagrams. So phase diagram gives us temperature and concentration. With overview of all possible changes to the microstructure of value compositions consisting of A and B atoms varying from 0 to 100%. Phases, homogeneous and heterogeneous system. As similar uniform components of a system are called phases. Phases are similar uniform components of a system. Homogeneous systems is only one phase, and heterogeneous several phases exist simultaneously. So there is occurrence of miscibility gaps. The components are separated from each other by phase boundaries. Coulomb curves and phase diagrams. On the left, we have a Coulomb curve. So there is a hold point. The temperature remains constant despite heat dissipation. There is a phase transformation. Dissipation of the latent heat. And there is a phase diagram on the right, which phase occurs at which temperature and concentration. So we need to define phase using temperature and concentration. Applies to thermodynamic equilibrium and also called very slow cooling. So in the cooling curve we have time and temperature in Celsius. So there despite heat dissipation, we have here several plateaus at these red temperatures where we have phase transformation. So first it's from liquid to delta ferrum, delta ferrum to gamma ferrum, gamma ferrum to alpha ferrum. So here we have a liquid phase, delta ferrum phase, gamma ferrum phase, and alpha ferrum phase. And here in our case, around 800 degrees, we have Curie temperature. So it's a point, so above that point, we have paramagnetic metal behavior, and less if it's below, we have ferromagnetic behavior. So here we have a small graph for different concentrations. So we start at 100% of component A, 0% of component B, and end 0% component A, 100% component B. We have here same temperature, and here we have marked with different colors phases. So dark red, or brown, it's a liquid phase. The green is liquid plus solid phase. And in dark blue, it's a solid state. And in these plateaus and transition points, we can transform in a phase diagram for complete solubility, liquid and solid. with liquidus line and solid line constructed using these transition points or plateaus. Of course, we need to take into account these concentrations. So here in the middle we have liquid and solid area. We have liquid with solid solution. Here we can also apply famous rule with metals. So the total mass, so the mass of liquid plus mass of solid is equal to mass. And plotted and certain temperature. So we multiply the mass of liquid times concentration liquid plus mass of solid times concentration solid. We got the total mass times C0 atom concentration. Result, we get a formula like solid mass of solid divided by total mass is equal to a level of liquid divided by level of solid plus level of liquid, and mass of liquid divided by total mass is equal level solid divided by level solid plus level liquid. So our level rule is mass of solid divided by mass of liquid is equal to level liquid divided by level solid. So like a proportion. And it can be also written like mass of solid times level of solid equal to mass of liquid times level of liquid. So in visual scale, we can illustrate it. So we have here C0. So it's a certain concentration. It's a 60% component B and 40% component A. And in our case, we have here a liquid level and solid level. So liquid level, here we have same temperature, and here is a mistake. Here should be concentration liquid, and here we have solid level, and here it's a solid concentration of solid. Right, solubility, liquid and solid. So here are illustrated different phases. And here we can apply formulas like solid mass divided by total mass is equal to concentration certain minus concentration of liquid divided by concentration solid minus concentration liquid. So in this case, it's component is 40. Sorry, component B it's 40% minus concentration of liquid 30% here. So concentration liquid 30% divided by 62 for this line percent of component B minus 30%. So concentration of solid and is equal to 31%. So for this line, we have similar formula. So here we have concentration certain 40% component B. So 40 minus 22. So it's liquid concentration. And 52 solid concentration minus 22 liquid concentration, and it is 60%. And concentration is 40%, B component, 60% A component. Here we have different temperatures, 6 different temperatures. So in for temperature 0, here we have 60% and 40% components. So, and the mass divided by mass total is 0%. Temperature 1 here on liquid slide. We have so component A concentration, liquid concentration 61% A and 39% B. Solid concentration 27% A and 73% B. And mass of solid divided by total mass is around 0% in second temperature. Here we have a concentration of liquid around equal to 70%, component A at 30% B. So solid concentration 38%. And 62% component B. So and total mass solid divided by total mass is equal to 31%. Temperature syntax 3. We have C liquid around 78%. And as a component B with 22%. So here it's 22%. And accordingly, it's 78% of component A. Sorry, 22% of component B here and 78% A. So the solid concentration is 48%. Here solid 48 and component B. So its concentration solid is 48 and here we have at this point, according to 52% component B. And the total mass of solid divided by total mass is equal to 60%. And here for temperature 4. So we use this line. This concentration liquid 85% to 85% of A here and 15% B, and concentration of solid is equal to 59% of component A and 40% B. Mass divided by M total is around 100%. Here's summary. So in metallic systems, the various possible phases are represented as a function of content, temperature, station temperature, in the form of phase diagrams. This is generally applied to cooling, so as long as the thermodynamic equilibrium can be reached at any temperature. The system, complete solubility in the liquid and solid state, the both components solidify with the hold point of other alloys in the temperature interval. Okay, king points during solidification or melting phase region, the concentration of melted solution change constantly with falling or rising temperature respectively. And state diagrams can be determined by characteristic points on cooling points. So there are hold points where temperature of cooling color remains constant until the phase change is complete. King points, these are typical changes of size in molten or solid solution region. They are caused by the released heat of crystallization. So latent heat is a released heat of crystallization. And here are some question and exercises. So the question first, what are the component and phases of an alloy? So component is a chemical element that builds the alloy, and phases are homogeneous solid or liquid bodies. Abrupt change of properties at interface. Name the difference between the cooling curves for metals and alloys. All metals solidify depending on the cooling rate at a certain temperature or holding point. Alloys usually have a solidification range. So king points in the cooling curve. Alloy consisting of two substances can only exist in two modifications. Name them and state the number of phases in each case. So it's a heterogeneous mixed, two or more phases, and a homogeneous uniform, one single phase. Condition must be met for a system to exhibit complete solubility in the solid and liquid state. So the first, equal crystal lattice, similar atomic size, or also similar lattice constants, minor potential difference, the redox series. So the redox potential is measured of the ability of the ions to accept and donate electrons, and similar valency. A valence is a minimum number of monovalent atoms that can be bonded with an atom of a chemical element. Homogeneous solid solution show higher strength values and a higher hardness than a poor component for certain composition. Why? The crystal lattice of the solid solution are disordered due to the different atomic radii. As this impacts atomic and dislocation movement. As a result, hardness and strength increase. Question 6. What characterizes as a start of solidification? And second, which phase precipitates at the start of solidification? Insertion between the perpendicular color line and the liquidus line. So it characterizes the start of solidification. And a solid solution with approximate 35% copper. So evaluate the proportion of phases and their composition on the upper and lower balance beam and explain. So using this formula we have discussed before, we get 18% solid solution with 38% copper and 62 nickel, and 82% of liquid or melt with 77% copper and 23% nickel. Here. So, and the third formula, 83% solid solution with 65% copper and 70% liquid melt with 94% copper and 6% nickel. As the temperature decreases, the melt becomes blended in nickel and enriched in copper. Shortly before reaching the solid dose temperature, the melt has a concentration of approximately 95% copper. The solid solution and the last question, what is the concentration of the solid solution after complete solidification and why? The solid solution, which initially forms a concentration of 35% copper and 65 nickel, at the beginning of solidification constantly changes its concentration by diffusion and finally exhibits the normal concentration of 70% copper and 30% nickel when the solid dose temperature is reached. In order for a homogeneous solid solution to form, cooling must proceed so slowly that the necessary diffusion processes lead to complete concentration equilibrium. So it's the end of the third part, and we can also look on this practical file about the lever rule. Here we have the single phase diagram with liquid dose line, solid dose line, and here we have lever on a definite concentration. So, and we can change. So in case if it's 50, we have 50 degrees temperature, and we find the points, intersections. So in liquidus case, it's around 30% orange and 86% solid. blue color. So here we have liquidus level, this orange. So it's 86%, solid dose concentration minus 50% initial. We have lever solid dose here is opposite with blue color. So we get it from this initial concentration 50 minus 13% liquid, and the total lever is 73%. So from the solid concentration minus liquid concentration. So the mass of liquid divided by total mass is around 49.3%, and solid divided by total around 50.7%. So lever, liquidus lever divided by total level, and here we have solid level divided by total level in percent. Here we can calculate fraction B in liquidus. So liquidus mass times concentration of liquidus, solid dose mass. It's fraction B in solid dose. So in solid times concentration of solid is 100% total mass A plus B. Here we can also change the delta of temperature, final temperature, initial temperature, fraction B, fraction A, mass exchange with a temperature difference, and concentration change with delta T atom is equal to minus 10 degrees Celsius. So we can change the initial concentration, for instance, to 40, 30, or maybe 10. And change temperature. Okay, so I think we will end here. Thank you for watching, and we will continue with other topics next time.